It's a pleasure to be here with Mojtaba. So Mojtaba is a PhD student at the University of Illinois at Chicago. He is interested in systems and networks, and he's currently advised by Professors Balaji Vamanan and Brent Stephens. So Mojtaba, take it away.
Okay, thank you very much. Thank you for the introduction. Welcome to my talk. So in this talk, I'm going to talk about mathematical operation in programmable switches and using TCAMs. So in this project, I collaborate with graduate student Kamal Shinde and my advisor, Dr. Balaji Vamanan, and my co-advisor, Dr. Brent Stephens at the University of Illinois at Chicago. So programmable switches enable new switch functionality, packet header modification in data plane and in network. Some use case examples are congestion control mechanism in network computation, distributed consensus monitoring, measurement, load balancing, and many other applications. And some of these applications are stateful. But the workflow for deploying switch program is the same for all of these applications. So basically, programmers start writing their program in P4, and then they compile their program and then put it in the programmable switch, and they put the programmable switch for test. So here is the architecture of programmable switches. In general, this architecture is common in programmable switches as it is explained in papers like Dominoes and forwarding metamorphosis. So there are different kind of components here, but I want to focus on two components that is important in this talk. So lookup table is the first one. So lookup tables compare input against the table and return the matching data. And then we have ALUs that are responsible for processing standard arithmetic operations, shift bits, header modification, and hashing operations. But unfortunately, ALUs in programmable switches are limited. ALUs can support addition and subtraction, can support left and right shift bits, they can support header modification and hashing operations, but they cannot support division and multiplication, which actually happens to be important in some application. So here is an example. So I've been trying to implement a rate limiter using counters in a P4 program. So basically my rate limiter try to emulate a queue using counters, and I will drop the packet if the queue size exceeds the drop threshold. In other words, I'm measuring the input rate of the packet, and I will drop the packet if the sending rate of the sender is more than a desired rate. So let's take a closer look at it. So at first I'm tracking the time, inter-arrival time of the incoming packets. Then I multiply this time by a rate, by the desired rate, and I will calculate the drain byte. And I use this drain byte to decide if I want to drop the packet or not. So as you can see, we have a multiplication here in this application. So I started writing my program in P4. I tested it on BMV2 and it was working. But when I was trying to test in pizza switches, I faced this error, which says expression too complex. And the reason is ALU on programmable switches does not support multiplication. And it appears that this is not the only application that needs mathematical operations. There are many more applications that actually need mathematical operation. So let's consider congestion control as an example. We have two interesting work called XCP and RCP, are rate control and congestion control mechanism. For example, XCP needs 4 floating point multiplication, and RCP needs 7 multiplication and division. But unfortunately, none of these approaches implementable in P4 switches or in commodity switches because they need mathematical operation. So many key applications require multiplication. So let's see what are the possible ways that we can actually have multiplication in a P4 switch. So one way is to actually implement the multiplication algorithm using addition and shift bits. So this approach will result in exact result, but the problem is this approach requires too many stages, especially if the number is very large. Another way is, so that approach is not practical. So another way is to use exact match lookup table, but unfortunately this approach also requires a prohibitively large memory, because having all of the different combination of the two numbers would require large memory. So none of these two exact multiplication is actually implementable and practical in switches. So what about approximate multiplication? So one way is to approximate multiplication using left shift. But the problem is this approach produces a large error. And the reason is, if you want to approximate your number with a number that the closest power of two number, it might be a far distance and it produces a large error, but it has a low overhead. So the only promising approach is actually approximate using lookup table. So in this talk, we will ask this question that can we emulate multiplication using reasonably sized lookup tables and provide error bounds? In order to answer this question, we propose an approximation approach for multiplication that with bounded maximum error and limited number of table entries. We also present analysis of maximum error and TCAM usage, and we derive the optimal number of entries for a given error. So here's the outline of my talk. So I already introduced my motivations in my talk. So I will talk about the design in detail, and then I will show you a few interesting results that I get from analysis. And finally, I will finish my talk with a conclusion. Okay, so let's start with the naive approach, with a naive solution to populate the lookup table. So this picture shows the abstraction of a lookup table. X and Y are the input and the Q is the output. So if you want to find the result of a multiplication for X and Y, you will look up that entry and you will find the Q and the TCAM. But unfortunately, this approach, as I said before, this approach requires a large number of entries. For example, in this case, X and Y and Q has 3 bits, and just for these 3 bits, I need 64 different entries. So one way to approach this problem is actually grouping these numbers such that numbers in the group are close, and each group has a group head, and then we will use this group head to calculate the product. But let's see, so in this way, if you group the number, we can reduce the size of the tables. So this is the first approach that we can group the numbers. So in this approach, we will match on n most significant bits. So in the example at the left, I have a number and I'm matching on 5 bits. So basically, if any other number in the list of my number follow exactly the same pattern, which means that the 5 most significant bits are similar to these numbers, they will be in the same group. So I have 2 examples here. I have a pool of numbers and I want to group them. So if I group these numbers together, we will see that the numbers that have the 5 most significant bits similar to each other will be in the same group. This approach is very simple, but unfortunately this approach produces a large error. And if you want to reduce the error, it requires a large number of entries. So in this example, I have my significant bit is actually 1 here. So as we can see, it actually divides the space of the variable x into 2. So but we have, there's another way to group the numbers in a more efficient way. So here we introduce adaptive precision that actually group the number based on the first non-zero significant bit. So in this example at the left corner, the first non-zero significant bit, we will find the first non-zero significant bit, and we will put all of the numbers in the same group if they have the first non-zero significant bit in the same position. For instance, in this example, we have the first non-zero significant bit in the second position. So basically all of the numbers that have the same feature will be in the same group. So again, my toy example, we can simply group the numbers together here as well. But we don't have to be limited to just the non-zero significant bit. We also can consider any number of digits after that first non-zero significant bit. In this example, I'm also considering one number after that, which is basically I'm going to match on 1 0, and every other number that have 1 0 in the same position of their numbers will be in the same group. So again, I have the same pool of numbers that I had in the previous example, and I will group them again. So as we can see, those two numbers in the bottom are in different group. So this is the way that actually the size of the group will changes when we increase the B. So in this example, I'm using a B equal to 1. So basically I'm matching on first non-zero most significant digit, which is B equal to 1. And this approach can actually provide bounded error. It has limited memory usage, and it has different precision for different groups. So once we group all of the numbers, we use LPM feature available in TCAMs to allow us to represent the group in the switches. As it's shown in this picture, the last box, we are using 1xx to represent 4 numbers that have a 1 in the most significant bit, for instance. So we're using the LPM to represent, to actually pack all of those groups into one entry in the lookup table. So the only remaining problem is how can we choose the group head? Because take this box as an example. So we have 1xx and we want to multiply it to 001, and we don't know what we put in the queue or as the input because we have 4 different options. We could use any of those numbers here. So the ideal approach, ideally we can actually have choose any of those 4 number, but ideally we choose the number that is close to average, and it's provable that if you choose this number, you will have the minimum error. I have some backup slide for this if we can actually see all of different kind of approaches. But for now, let's accept that the average, that the number that is most closest to the average is the best for to be at the group head. So using the group head, we're choosing the group head here, which is the closest to the average, and then we will calculate the output of this multiplication. So in the last box, we can see that all of the variables are 1, 0, 1. Okay, so this is the table abstraction that I showed at first, and we know that the naive solution produces 2 to the power of 6 or 64 different entries, but this is what we have right now. So we basically reduce the numbers from 64 to 16, which is 75% less than the naive approach. And we have the 0 or very low error for a smaller number, and when error increases, then the value increases. So here's some formulation. If someone is interested in the formulation, we have the formulation to calculate exactly the number of entries that is required to populate the table. And also I have the error, which actually shows in percent, it shows how much lookup table overestimate your real number. And I have some proof and examples in the backup slides. Okay, so let's talk a little about the evaluation and the result that I got. So for simplicity, let's assume that X and Y and Q, they're all 32 bits. They don't have to be the same, but let's assume that they're all 32 bits. Also, we assume that bx and by, which is the adaptation factor for x and y, are the same in all of the couple of graphs that I'm going to show you. And I will change the value of b from 0 to 32 to see how the error and how the error changes and how the number of entries will change. Here's the first graph. So the x-axis shows the adaptation factor, or b, and the y-axis shows the required table entries in megabyte. So as we expect, when the adaptation factor increases, basically when I move from 1 to 2 to 3 to 32, the required table entry increases because we're actually generating more number of groups. And it goes all the way to get to almost similar to a brute force. And we can see that roughly around 20, when the b is equal to 20 or less, we have an acceptable amount of table entries in the lookup table. Here is another graph. So in this graph, x-axis is again the adaptation factor, and y-axis is the maximum error. As we expect, when b increases, the error also increases because simply we are having more number of groups. And we can see that we have a very low error to the end of the interval. And we also noticed that when the b is around 10 to 20, the ideal value for a b is, in our experiment, is when the b is around 10 to 20. And it depends on the available memory in your system, available TCAM in your system, that which one of these numbers you should use. So to conclude, we design an approximate approach to support multiplication using lookup tables, and we are working toward implementing a P4 pre-compiler that converts a P4 program with multiplication to a P4 program with lookup tables, given the accuracy or the error and the table size. Thank you very much for listening.
Thanks, Mojtaba. That's really cool. I guess I was wondering, like, when you talked about things like rate limiting and sort of doing this multiplication. I mean, so there are like policers that exist on switches today, like which have to actually do this computation of, like, do we have enough? So for example, like a token bucket policer or a token bucket shaper, kind of figure out, okay, do we have enough tokens at this point for a packet? And presumably those require multiplication too. So would you have any insight into like how those are actually implemented? I mean, is it just the fact that they are kind of fixed function components, and maybe the kind of guarantees you expect from them are different? Like, so how are those things actually implemented?
So implemented in the P4 switches?
No. So they don't have to be P4 switches. So I mean, at least it's my understanding that there are kind of routers in the internet that actually implement some sort of token bucket policing. Oh, hey Brent, I didn't see that you were here. Hello. So yeah, I was wondering. I mean, is there something kind of conceptually different about those multipliers, or like, I guess I was trying to understand like how those things are actually implemented, and
So I think I can
some of that
maybe help Moji out if that's fine.
Sure.
With this. So I think there's sort of a few things going on. One of them is maybe this idea that the existing routers that are implementing this sort of thing are doing it in a very fixed function way, because they don't have to have sort of this pure programmability. They don't have necessarily the same overheads. But I think another big thing that we are trying to do is enable multiplication and then really further arithmetic where both of the variables can be programmable from the data point. essentially. So we want the multiplication to be completely accessible within the data plane pipeline, which is maybe a little bit different than some of the existing functions. But that's really, you know, I'd say probably another project that sort of this spun off of.
Interesting. So it's possible that some of the existing solutions may have assumed the value of one of these, you know, one of the two numbers that you're actually multiplying and kind of computed the table as a result. Okay, that makes a lot of sense. The other interesting thing that I was reminded of is actually, so when we were in high school, you know, sometimes like we weren't actually used to, we weren't allowed to use calculators. So the way we used to do multiplication was by using logarithms, right? Like, so logarithms turn multiplication into addition. So actually, when you were describing kind of your design space of, you know, like, okay, we can do kind of exact multiplication or approximate multiplication, and here are the different strategies. I was kind of thinking, like, you know, if you're using a lookup table, you know, maybe you could use kind of a logarithmic lookup table. Like, have you considered approaches like that? I mean, do you think it might work?
Mind if I answer some of these, Moji? I think that's a really interesting idea we should investigate, but it's sort of a first glance for just a multiplication. It may be potentially higher overhead in terms of number of stages. So you have to do the pre-processing and post-processing. And so maybe I think my expectation is that approach, when we analyze it, may require less forwarding table state to perform the logarithms, but it has higher costs and stages. So I think it's a very interesting suggestion. And it's sort of getting at this other idea about really not just even multiplication. You know, logarithms are needed by some functions, and then they're used for further math. You know, at what point should things be in lookup tables and multi-stage? And so that's really, I think, the future of this project.
Cool. Yeah, this sounds quite exciting, actually. I think if you have logarithms, you could certainly also do division. I mean, you could kind of get that as well, because it's, you know, again, like division is going to be like subtraction of logarithms. So yeah, that's kind of interesting.
Yeah, I think
cool.
The big open problem in this space is sort of this idea of our error. We were able to have the same bits of precision and the same error everywhere because multiplication is linear. And so we're really excited for looking at some of these non-linear, more complicated, more variables, especially things where we maybe even know the domain and range in advance and do optimization.
Right. Certainly, I could imagine if you knew that, you know, certain values have like more, you know, they sort of appear more frequently in your distribution of numbers that you're multiplying. You know, maybe the RTTs, you know, don't go all the way from 0 to 1 million. You know, maybe they go from 0 to 10,000. You know, that could certainly allow you to like focus more of your table space on those numbers which actually require more precision, and kind of, you know, allocate less for the others. So yeah, I think there's a lot of interesting stuff you could do. Cool. There's definitely a lot of possibilities, I think. So where do you think, you know, what other kinds of use cases are you thinking of supporting? It seems already that you have like a list of use cases like, you know, kind of congestion control, you know, some of these control laws that require multiplication. Were there kind of other use cases that you would think might use this sort of mathematical capability?
You know, I think Moji can chime in here at the end if he has any toy applications, but this is sort of one of the reasons that we are, you know, previewing this at this roundtable is, you know, our initial sort of other functions we're interested in are things like XCP, RCP, but really we're trying to find what, you know, the community wants in these types of applications to get some sort of, you know, large feeling about what these class of different arithmetic operations we're trying to perform are. And so, you know, this is a good thing where we're very interested in hearing what other people think are their sort of pet and toy math operations they want to do in P4.
Yeah, one potentially interesting direction is also, so if you think about all these synthesis-based compilers that, so for example, like Domino, when you have like a set of instructions that exist on the hardware and you're trying to fit a given program to kind of be implemented using those instructions, I feel like the way you think about that problem might have to change if you include, so multiplication as one of the possible instructions you could use, right? I mean, of course, it's not like a single ALU, right? I mean, you're actually using ALU along with a bunch of different tables and, kind of configuring those tables and so on. But I think it's kind of an interesting way to think about how you implement computation itself. So I think so at some level, when you talk about multiplication as just a primitive you want to implement, there is some optimization you could do over there. But there's also the higher level, kind of going one level of abstraction beyond that. You can actually think about a program that can, that has multiplications inside it that could then, sort of there's like a more global resource allocation problem, which is like, how do you actually kind of put together, all of the other instructions that the program might need along, it's the rest of the tables that the program needs, along with all the tables and the ALUs that your multiplication itself requires or your division itself requires. I think there's kind of interesting resource allocation problems that you can think about.
Yeah, I mean, that's exactly this sort of multi-stage versus table size trade-off that unless you know the full rest of your program and your target, you're not able to correctly optimize. Yeah,
right. Cool. Yeah, I didn't have too many other thoughts or questions, but feel free to kind of talk about things that maybe you had questions for the community or sort of thoughts for the community. Like if you want to share those, you could do that.
Yeah, I mean, I think it's just like I expressed, we're sort of interested in seeing how other people in practice are writing applications that require multiplication. We're sort of interested in just hearing about other applications. We're hearing about other people's approaches to solving these problems. I think in general, it's this sort of idea that anyone who's writing P4 programs is likely to come against this problem. So we're trying to have somewhat of a community motivated solution to this, I think. And really, I think if it wasn't clear, we're sort of targeting some sort of open source tooling to release to help people out who are P4 programmers.
Cool. I hope you get a lot of kind of ideas when people watch this. So cool, awesome. Thanks a lot. Thanks Mojtaba for the talk.
Thank you very much.
All right.